Okay, hello students. Let's start with the remaining topics of oscillator module. So we have seen so far what is the need of an oscillations, what is its criteria, and we have also seen the circuit diagram working and frequency for RC phase oscillator, and briefly we have seen Wien bridge oscillator, the circuit diagram. Now we'll move our attention to LC oscillators. So yeah, write down LC oscillators. A word or two on LC oscillators, and then we'll move on to how do the LC tank circuit produce oscillations. So let us write. So they are also called as RF, radio frequency oscillations, or they are also called as tuned oscillators, or tank circuit oscillator. So they have many names. They are used to produce an output, a sinusoidal output mostly, of a frequency ranging from a very high value, let's say greater than 20 kilohertz to few megahertz, okay, or tens of megahertz. So that's the value which they have, and they have two parts. Part number one is amplifier. So mostly we will be using a BJT amplifier, a voltage amplifier basically. And the second part is LC tank circuit. So this will be my feedback network. This will be my feedback network. You remember, when we started oscillator, we have started in a block diagram approach where we have used that we require an amplifier and the feedback signal should be additive. This is my feedback network. This is the output of the amplifier given to the input of the feedback network, and output of the feedback network feed it back to the input of the amplifier, and this is my feedback signal. It's get added. So here we have having a positive feedback. Okay. So it's supposed to give you output which is sustained oscillations like this. Yes or no? And the overall phase shift. What is the criteria which we have to follow? The overall phase shift around the loop. So let's say the gain of amplifier is A1 and the gain of feedback network is K. So the phase shift between A1 and K should be 0 or 360 degree. Okay, and the magnitude of A1 into K should be greater than or equal to 1 at the start. So these two criteria should be followed. Also, now why this is called as a LC oscillator, because the feedback element, here we can write the feedback, why the name LC oscillators? The feedback network consists of inductor and capacitor. Inductor is L and capacitor is C. Okay. All right. You're writing along with me. Yeah. So here we have to learn one thing now. That LC tank circuit. That is our focus now. So we'll talk about LC tank circuit. What happens when we connect a capacitor and an inductor together? So what it will produce. So let us go to the next topic. Are you all ready? Okay. So this is the background LC oscillators. Why they are called as LC oscillators? Because the feedback network consists of an inductor and a capacitor. Okay, and it uses a positive feedback. It has two parts, amplifier and a feedback network. So overall phase shift should be 0 or 360-degree, and the product of their individual gains should be greater than or equal to 1. So these criteria LC oscillators should follow. And there are two types of LC oscillators which we are going to study. The two types are, one is Colpitts oscillator, other is Hartley oscillator. Okay, so we'll study them one by one. Let's go to the next topic now. So the next topic is how an LC tank circuit work. So let's go to that. Write down how LC tank circuit produce oscillations. So LC tank circuit also produce oscillations, but these oscillations are not sustained. That's why we require an amplifier. So this question we have to answer. Okay. Alright. So the LC tank circuit, let's write few statements over here now. The LC tank circuit produces electrical oscillations. The LC tank circuit produces electrical oscillations of any desired frequency set by values of L and C. Okay, it produces oscillations set by the values of L and C. All right. And for the LC oscillations, the frequency can be shown that it is given by 1 upon 2 pi square root of LC. This you don't have the derivation, but you should remember. So for all the LC oscillators, this will be the frequency formula, where the values of the frequency will be set by LNC component. Okay. Now let us see how does an LC tank circuit work. So you have heard of capacitor and an inductor, right? Both are energy storage elements. So your capacitor C and L both store energy. Okay. So what does the capacitor store energy? Capacitor store energy, let us write this point. Inductor L stores energy in its magnetic field. Inductor stores energy in its magnetic field whenever current flows through it. Whenever current flows through it. Okay. So inductor stores energy in the form of magnetic field whenever current flows through it. And then we will write about the capacitor. The capacitor C stores energy in its electric field, in the form of its electric field, whenever a voltage is applied across its plates. Whenever a voltage is applied across its plate. Okay. So inductor, how does an inductor look like? Can you inform? So inductor is like a coil, right? So it's like a coil. So this is an inductor determined by L. So it stores the energy in the form of a magnetic field, which is like this. Okay. So anyways, this is what I was conveying you all. This is an inductor consisting of coils. And then we have a capacitor. This is the symbol of a capacitor. There are two parallel plates. This is the C. So it stores the energy in the form of its electric field. So there are positive charges on one side and negative charges on the other. So it stores the energy in the form of an electric field. Electric field is directed from positive to negative, like this. Okay. So that's how the capacitor stores the energy across itself in the form of electric field, and inductor stores the energy in the form of magnetic field. Alright, can we move ahead now? Everyone has written up till here? Yes or no? Okay, so we know now that inductor, both the elements store energy. Now let's say that you have an capacitor. Now let's draw the circuits. So we have a fully charged capacitor. So let's say we have a capacitor and we have an inductor. They are connected to a switch. You know, understand switch, right? Switch can be closed or open. So this is a switch. This is a capacitor. This is an inductor. And then we have another circuit where we have, let me just complete this. So this is the LC tank circuit as an oscillating circuit. So here capacitor is pre-charged. Capacitor is already charged state. Like a battery, right? Battery is already charged. So capacitor has a polarity always across it. So let's say it has a positive polarity over here. So it is carrying some voltage. Okay. Capacitor is charged from a DC source separately. Okay. Capacitor is already charged. So what they do is they connect a DC supply and they connect it to the capacitor to charge it. So capacitor will charge to the full capacity of the battery. Let's say the battery voltage is 10 volt. So capacitor is already carrying a voltage of 10 volt across it. Okay. So capacitor is already charged, previously charged, having this polarity, plus above and minus below, in the upper plate and lower plate. Okay. So now as the switch is open, it cannot discharge. See, capacitor charges and discharges, right? It charges and it discharges. You know that. You must be knowing that thing, right? This is charging. This is discharging. Okay. So a capacitor will charge, will store the charges and will release the charges when it finds the open part, closed part. So capacitor is already charged. As the switch is open, it cannot discharge through L. Okay, that means it cannot release its energy. Now it can discharge when the switch is closed. So let's say we go to next circuit, next part of the circuit where we have C and there we have a inductor already present. This is L and now we close the switch. Now what will happen? So here switch is closed. We call it SW. So the switch is closed. What will happen now? Tell me. So as the switch is closed, the capacitor discharges. So all the charges which were stored in the capacitor, here there were charges, right? Stored inside the capacitor, positive above and negative below. They will slowly discharge. So this will slowly discharge like this via the inductor. Okay. So they will slowly discharge. So slowly discharge in the sense 10 will become 9, 8, 7 until it becomes 0. Okay. So the capacitor will keep on discharging. Alright. So here we can say C discharges through L because the switch is closed. But the capacitor, first of all, it was charged, it was holding all the charges. Now it's releasing all the charges. So capacitor is discharging. So at the same time, when the capacitor is discharging, there is this current flowing in the circuit now. Okay, there is this current flowing, which is IL, current flowing through the inductor. This is called as discharging current. Okay, so capacitor gets discharged. So current starts flowing through the inductor, through the inductor L. So what the inductor will do? Inductor will store the energy now. Slowly and steadily, this discharging current will keep on increasing. Okay, so inductor will try to store the energy like this. See, will try to store the energy. So the more it discharges, the more inductor will charge and store the energy in the form of magnetic field. So this is the magnetic field which I have shown over here. Okay, this is the magnetic field. The current starts flowing in the circuit in the form of discharging current, and that discharging current will set up the magnetic field around the coil. So this is the magnetic field. Okay, so it will set the magnetic field around the coil. Because of the inductive effect, the current grows up slowly towards the maximum value. So this situation occurs when the capacitor is fully discharged. So the electrical energy across the capacitor is completely converted into your magnetic energy. So when C discharges fully, so what is happening is, as soon as the capacitor is losing its energy, inductor is gaining the energy. Okay, so when the capacitor was discharging, inductor is charging. Okay, so slowly and steadily this magnetic field becomes stronger and stronger. All right, are you able to understand? So when the capacitor discharges fully, what will happen now? Yeah, when the capacitor is discharged fully, the electrical energy in the form of electric field across the capacitor is is converted into magnetic field around the coil. Okay, converted into magnetic field around the coil, around the inductive coil. Okay, so that means once the capacitor is fully discharged, magnetic field around the coil, around the inductor, begins to collapse and produces a counter EMF. Okay, so as now L is fully discharged now. So what it will do? What this will do now? L, capacitor में सारे charge चले गए. All the charges are gone. So capacitor is fully drained out, whereas inductor is fully loaded with all the energy in a form of magnetic field around it. Now when that happens, now the capacitor slowly discharges again. So पहले capacitor was charging, capacitor was discharging, the inductor was charging back, and now the inductor is discharging. So what will happen is, when the electrical energy across the capacitor is converted into magnetic field around the coil, once the capacitor is completely discharged, magnetic field around the inductor begins to collapse and produces a what is called as counter EMF. Okay, you must have heard of this formula: VL is equal to minus L di by dt. Yes or no? Inductive voltage across the inductor is given by L di by dt. Now, this current was continuously changing. Now it produces a counter EMF. So according to the Lenz's law, counter EMF keeps the charges moving in the same direction. Okay, so the counter EMF will keep the electrons moving in the same direction. So that means what? Now the capacitor starts charging again, but it starts charging in the opposite direction because this is counter EMF. So now the capacitor starts charging in the opposite direction. So let me show it over here in another diagram. So pehle it was charging in plus minus. Now in the new case, when the inductor is fully charged, now it will discharge. So now it was fully charged with this magnetic field around it. It will slowly discharge now like this. This is the magnetic field. Okay, now it will charge in the opposite direction. So capacitor will slowly build the charges like this. See, the polarity is changed because capacitor is now charging in the other direction. So according to Lenz's law, these charges, the counter EMF will charge the capacitor in the opposite direction. So now slowly and steadily the capacitor is getting charged in the opposite direction. Okay, so slowly and steadily, as the capacitor is charging in the opposite direction, the magnetic field around the inductor is collapsing. So now we can say C is charging slowly, charging in the opposite direction with opposite polarity. okay, across its plates. So when the C is charging, what happens to the inductor? The inductor L, the magnetic field across the inductor L, I mean we can say in short, inductor L is discharging. What do you mean by inductor L is discharging means? Inductor L is discharging means what? It will the magnetic field around the inductor L is collapsing. Okay, so when the capacitor is fully charged, the magnetic field around the inductor is collapsed completely. Okay, so after this, the switch S, we have a switch S, right? Okay, the switch S is closed. All right. Now when the switch is open again, let's say the capacitor is fully charged with opposite polarity. The switch is open now. Now the capacitor will not discharge. Okay, capacitor will hold discharge. Now when again the switch is closed, so now capacitor will discharge with the opposite polarity. So over here we can say here C starts to discharge, but it will discharge in the opposite direction. Okay, not in this direction, this direction. So that again will set up the electric field, magnetic field across the inductor in the opposite direction. So what will happen is after the switch is closed over here again, okay, the capacitor starts discharging in the opposite direction, so that the charges now move from plate to plate positive to negative. Okay, so the electric field starts collapsing as the capacitor starts to discharge, and this will build up the, so here the capacitor is discharging, now L is charging. So whenever one component is discharging, the other is charging. Okay, so the magnetic field starts to build up again in the reverse direction. So L is charging in reverse direction now. Okay, so the above sequence, so basically the above sequence of charging and discharging, please write this point, above sequence of charging and discharging of a capacitor, C and inductor L results in energy being alternatively stored in the form of electric field in a capacitor and magnetic field in the form of magnetic field in an inductor, in an inductor L. Okay, so the above sequence of charging and discharging will go on happening. Okay, of a capacitor and inductor will result in energy being transferred, alternatively stored in the form of electric field and magnetic field. So this interchange of energy, between L and C continues, and it results in the production of oscillations. So ideally you should get oscillations which are like this. So ideally you should get oscillations which are sustained. Okay, but in a practical circuit, so right, but in a practical tank circuit which consists of L and C, but in a practical LC tank circuit, Oscillations are damped oscillations. What do you mean by damped oscillations? I'll tell you. Because of losses in L and C. Okay. So what do you mean by losses in L and C? L is not a pure inductor. It has a small resistance. So whenever we say L, practically we draw this coil, right? But this coil is also made up of some material, so that will have small resistance. So this resistance contribute to losses. Okay. So there are losses in a practical LC tank circuit. Oscillations are damped because of losses in L and C. So practically, how are the oscillations looking like? Damped oscillations like this. It slowly die out depending upon how small or high is the value of this resistance. So therefore, the amplitude of oscillations, because of these losses, because it's not a pure inductor or a capacitor, the amplitude of oscillations reduces gradually, okay, and reaches zero finally. All right. So the LC tank circuit produces this type of oscillations, which are not sustained at all. That's why we are going for Hartley or Colpitts oscillator. Okay. So did you understand this, students? Yeah. Now I'll show you a video. Since I have already explained this topic, the video is explaining the same. So let me play that video for you all. It's the LC oscillation animations.
If you connect a charged capacitor across an inductor, you will see a beautiful energy exchange take place between the two elements. These energy oscillations look as if the capacitor is saying, "You take the energy," and the inductor then says, "No, you take my energy." Why don't any of these elements store the energy and become settled? Let's have a look at the interesting physics behind these oscillations.
So over here, this is my capacitor, okay, two-plate capacitor, and this is the coil, inductive coil. As you can see, these are the magnetic energy, okay, and this is storing the electrical energy, as I've already told you. So capacitor will store energy in the form of electrical energy, and inductor will store. This is my coil, right? And this coil will have some resistance. So this inductor will store the energy in the form of magnetic energy. Now listen to it carefully.
And some of the applications. Before diving into the LC circuit, we need to understand a simple circuit, a capacitor-resistor circuit. The capacitor is fully charged initially. Let's introduce a resistor into the circuit.
You know what is a resistor, right? Okay, resistor is an energy dissipator. So let's see a simple example of a RC circuit first.
Here you can observe
So the capacitor is fully charged now.
that initially the current flow is at the maximum and then it sharply decays with time. This is expected because at the beginning the charge difference is at the maximum, so the current has to be at the maximum. Now let's see what will happen if the resistor is replaced with an inductor. Here again, the capacitor is fully charged initially. It's quite logical to expect that there will be a huge current flow at the beginning, and then the current flow would reduce as in the previous case. However, this will not happen in practice. An inductor develops EMF across it, based on the change in current flow.
This is according to the Lenz's law. VL is equal to minus L di by dt.
This means that a drastic change in current is not possible across the inductor, as in the previous case. Now the current flow starts from zero and increases to the maximum, and then comes back to zero again. In an inductor-capacitor circuit, the current flow varies.
So as you can see, the charges, electrical energy is getting reduced over here, and here the magnetic energy is getting on increased. Okay, so when the capacitor is discharging, the inductor is charging now.
Variation has to be gradual, and here we can see that the current flow in the LC circuit is shaped like a sine curve. Let's look at the electron flow animation once again. The current in the circuit starts from zero and gradually achieves the maximum value. In the next 1/4 of a time period, the current from the capacitor starts to decrease, resulting in another change in current. At the end past the inductor, it will have the opposite polarity to the initial EMF. This reverse EMF charges the capacitor with the opposite polarity. In the next half of the time period, the capacitor will be fully charged with the reverse polarity. This also means that the current flow will be in the reverse direction for the next half. Hence, in an ideal circuit, this back and forth flow of current would continue to charge and discharge the capacitor and form endless oscillations of energy.
So these are the ideal oscillations which are produced.
However, practically, we can never achieve such ideal
So these are called as undamped oscillations, as I've already explained. So these are practically never realized.
behavior due to the presence of resistance. The resistance causes energy decay in the form of heat. This means that
So where does the resistance come from? As I've already told you, this inductor is not a pure inductor. It will have a small, these are made up of windings which are made up of some material, and that material will have resistor. So the resistor will be the cause for the undamped oscillations. Okay, so here the oscillations are undamped.
in a practical circuit, the oscillations will die out eventually. As we increase the resistance, the oscillations die out very quickly as
See, as you can see, if the resistance of the coil is more, the oscillations will die out
shown.
faster.
If we increase the resistance further to some critical value, there would be no oscillation at all. Underdamped LC circuits have many applications in industry.
Okay, so this was the small demonstration of LC oscillator. I hope it is clear now, everyone. What does the circuit do? Any doubt, anyone? Can someone give a verbal confirmation you have understood the topic? Yeah. So what is the outcome of a LC oscillator? The LC oscillator, LC tank circuit, sorry. So we have a LC tank circuit consisting of L and C. So what is the outcome? Outcome is underdamped oscillations like this, which will die out soon. So what we do is we put this LC tank circuit inside the feedback network, and then we apply the amplifier to it. Okay, so that will eventually, when they are decaying, it will again amplify this, and bring it to sustained oscillation. So that is a plan. Okay, everyone. So that is how that LC tank circuit works. Now let's go to Hartley oscillator. Everyone, let's write down the topic of Hartley's oscillator. So what is the concept? We have an amplifier with a gain A1. We have a feedback network with a gain K. The feedback network is the LC tank circuit, and no external input is applied. Only the amplifier is powered with the VDD. Here we have V out, and we know the LC tank circuit will produce the oscillations, right? But they will die out. These oscillations produced over here will die out. So what it will do is these oscillations have been provided to the amplifier. The amplifier will amplify that oscillations, and then again this will be feedback to the feedback network, and again back to the amplifier until we get a sustained oscillations, that is A1 into K becomes almost equal to 1. So unless you have these oscillations, steady state oscillation, this process will go on happening. All right, so that's the funda of your that's the working principle of your Hartley oscillator. Now everyone please draw the diagram of an LC oscillator. Are you all ready? So first we'll go for the circuit diagram. So write down first case circuit diagram, Hartley oscillator. Sorry, circuit diagram. So first we'll draw the amplifier network. Yes, yes, you can ask your doubt. Yeah, yeah, you can ask your doubt. Hello, who has the doubt? Please go ahead and ask your doubt, please. You can unmute and speak. Hello. You can type the message. What is wrong? What is your doubt? Or what is your query? Can you? Okay, in the meanwhile, draw the circuit diagram. I hope he will ask the doubt again. So first of all, we'll draw the amplifier network. The amplifier, as we know, it's a voltage amplifier. So it's a common emitter amplifier which we have drawn before. So this is my amplifier. Alright. This is VCC power supply. R1, R2, RC, RE and CE. So this is my amplifier. Okay. So this is my amplifier network. This block is my amplifier. Now we connect it to the LC tank circuit. So LC tank circuit I'm drawing in blue color. So we connect it over here, LC tank circuit, like this. So you have you have capacitor. Then here you have two inductors, one over here and one over here. This is connected to ground. This is L1, L2 and this is C3. And the feedback signal is from here to here, like this. So this is providing the positive feedback. Okay, this is the feedback signal. And this, let's complete the circuit. So you can have a capacitor over here and this is my output. This is CO plus minus V out. So here we are supposed to get a sustained oscillations at the output, like this. And this of higher frequency. The frequency of these oscillations will be high. So high frequency oscillations will be produced, periodic oscillations at the output of Hartley oscillator. So this is my Hartley oscillator. So where is my LC tank circuit? This is my LC tank circuit. This is my feedback element basically. So this is my amplifier and this is my LC tank circuit. Okay, or we can say feedback network. Okay, any doubt anyone in this circuit diagram? Please draw the circuit diagram, please. Yeah. Everyone ready? Can I proceed with the explanation and the working? Completed the circuit diagram? Yes, no? Okay, can I start with the explanation? Hello students. So Hartley oscillator consists of an amplifier. Let us write the description now and then we write the working principle. So we write description. Let's start writing. Second part is description. We'll write the entire answer now only because I mean that is what we have decided earlier. So let's go with the description. So so write down Hartley oscillator. I hope you have completed the circuit diagram. Hartley oscillator, or we can write it consists Hartley oscillator consists of two main blocks. Number one, amplifier. Now amplifier में bracket लिखो, common emitter BJT amplifier is used. Okay, and second block is feedback network. Feedback network. So it is a LC tank circuit. So feedback network is a LC tank circuit. Okay, the amplifier, next point लिखो, amplifier provides has a voltage gain A1, and the LC tank circuit gain is K. Okay, so amplifier is the common emitter BJT amplifier, feedback network it is an LC tank circuit, amplifier has a voltage gain A1, and LC tank circuit gain is K. Okay, completed up till now. Can I go to the next point? Now we'll go to working principle. Third one, working principle. Let's write the first point. Yeah, the the LC tank circuit, the LC tank circuit provides a phase shift. So LC tank circuit provides a phase shift of 180 degree. Okay, the amplifier block produces a phase shift of again 180 degree with its input and output. So therefore the total phase shift is how much? Can you tell me? 180 plus 180, that is 360. Okay, so our number one Barkhusen's criteria is satisfied. That is the gain of the feedback net. The phase shift between the amplifier and the feedback network should be 0 or 360 degree. So this criteria is satisfied. This criteria is satisfied. Okay, are you understanding? Now, have you written up till here? Everyone, please respond, or you require some time. So the working principle over here is the LC tank circuit provides a phase shift of 180 degree between its input and output, and amplifier produces a phase shift of another 180 degree. Okay, ready? So here we have a variable resistor RC. RC is a potentiometer. So RC is a variable resistor. So by adjusting the value of RC, third point we can write, Resistor RC is used to adjust amplifier gain A1. Okay, and what is the gain of the feedback network? The gain of feedback network is K. Okay, so how does the A1 into K criteria is satisfied? So what we do is, this is satisfied. You are listening? So gain of the amplifier, that is A1, is adjusted. It's a resistor, right? It's a potentiometer, so it adjusted such that, so we adjust the value of A1 such that A1 dot K is greater than or equal to 1. Okay, so the gain of the amplifier, and that is possible by changing the value of RC. So gain of the amplifier is changed by changing the value of RC, and when you do that, this A1 into K is greater than or equal to 1. So until you obtained gain of the amplifier can be changed by changing the value of RC until you obtain the sustained oscillations. Are you understanding? So here we can also say the LC tank circuit not only provides the undamped oscillations, LC tank circuit provides itself provide underdamped oscillations, right? Like this. तो वो तो है ही. This provides underdamped oscillations which are then amplified by the amplifier. Okay, which are later amplified by the amplifier. This LC tank circuit has another role. This is job number one. Job number two is it also acts as a resonant filter. So it will pass only a desired range of frequencies. So it will also act as a resonant filter that passes only desired frequency of oscillations. Okay, desired frequency of oscillations. So this is the working principle. The LC tank circuit provides a phase shift of 180 degree. Amplifier provides a phase shift of 180 degree. The gain of the amplifier is adjusted by adjusting the value of RC until the gain of the amplifier and the feedback network is greater than or equal to 1. Now the total phase shift around the loop is also 180 degree, 360 degree or 0 degree. And we have a positive feedback involved. So all the conditions of oscillations are met. Okay. Now we'll go to the working. Everyone writing? Yeah? Hello, can you give me a feedback? Yeah. So again, there might be an inherent noise. There is no external input, huh? No external input applied, AC input applied to the oscillator. So maybe there are some small noise voltage also appearing over here, starting as a trigger for oscillations. So let's start. So LC tank circuit itself produces oscillations, but that trigger should come from somewhere, right? So let's start the working with the working. Working is point number 4. So write down please. Point number 1. When the circuit is energized, when the circuit is energized by switching on the DC power supply, by switching on the DC supply, small undamped oscillations small undamped oscillations and or small noise voltage, okay, appears small undamped oscillations are produced by the LC tank circuit or and or small noise voltage appears at the base of BJT. See, here it is. So there are some underdamped oscillations which are, you know, the LC tank circuit is providing. These oscillations and coming and reaching over here. So they might join up with the already present noise voltage, inherent noise voltage in the BJT, and these oscillations will be amplified. Let me just draw it properly. So my bigger amplitude, smaller and die out. So these are underdamped oscillations. They are no use to it right now. So what it will do is it will amplify this small noise voltage. Okay. So we can say collectively this underdamped oscillations which are produced from the LC tank circuit, it's collectively termed as a noise voltage. Okay, and they are appearing at the base terminal. This is the base terminal of BJT. Base terminal of BJT. Okay, this is my BJT. This is collector, this is emitter terminals. Okay, so these oscillations are appearing at the base terminal. Now let's see what happens to them. These small noise voltage or underdamped oscillations are further amplified. To amplify, what it will do, it will amplify with a gain A1 by the amplifier. Okay, so this small noise voltage in the form of underdamped oscillations are further amplified with a gain A1 by the amplifier. Okay, and then they are fed back to the LC tank circuit. So the amplified uh, noise voltage is applied. So these gets amplified, right? So you get a bigger oscillations, but it is still dying out. But you're getting this bigger and bigger in amplitude because it's amplifying with a gain even. Okay, this again fed back to the feedback network. It will again produce underdamped oscillations, but with a higher amplitude. And again, it will be given to the amplifier. Amplifier will, you know, will will amplify it with a gain even. So slowly and steadily, you will get this waveform. See what I'm drawing until you get a sustained oscillations of high frequency. So this is how what the output of Hartley oscillator will look like. Okay, yeah. So initially due to the underdamped oscillations or noise voltage, and then once it picks up and reaches the limits of the nonlinearity in the circuit, it will attain sustained oscillation. So where it is having constant amplitude. All right. Anyways, we are writing over here these small noise voltage are further amplified with a gain A1 by the amplifier, and then they are fed back to the LC tank circuit. Okay, so at the output of LC tank circuit, small underdamped oscillations, we can say small oscillations which are amplified by the amplifier, right? Small oscillations are produced which are again fed back to the base of BJT and are amplified again. So these oscillations are fed back and they are amplified again. So this process wherein we have a small underdone oscillations at the output of the tank circuit being fed back to the base of the BJT and then is amplified with again fed back to the LC tank circuit. This process will go on until we obtain a sustained oscillations like this of constant amplitude. So please write down point number 4. So this process continues till the gain of the amplifier A1 is sufficient to produce sustained sinusoidal oscillations. Okay, so this happens sinusoidal oscillations at the resonant frequency. So LC tank circuit will work at a resonant frequency, at a resonant frequency of the LC tank circuit. So LC tank circuit LNC will decide the frequency of oscillations. So in this way, sustained sine wave oscillations are produced due to positive feedback from the LC tank circuit, which is the feedback element. Okay, right? Write the last point. A stable sinusoidal high frequency oscillations are obtained at the are obtained at the output of Hartley oscillator by varying potentiometer RC. Okay, so as a result we get a constant frequency and amplitude waveforms. So this is the working of LC oscillator. Okay, everyone understanding? So a stable sinusoidal high frequency oscillations are obtained at the output of Hartley oscillator by varying potentiometer RC. The result is a constant frequency and amplitude waveforms. So the waveforms at the output will look like this, exactly as I have shown over here. This one. So this is the output of Hartley oscillator. A high frequency sustained oscillations. Now next is frequency formula. Keep on writing. Point number 5. frequency of oscillation. So as I have already informed you all before, the frequency of oscillations will be given by, what is the formula of the LC tank circuit? 1 upon square root of LC, 2 pi LC. This can be derived for LC oscillators. Okay, but what is LNC will come over here. So if you see carefully, there are two inductors. So these two inductors are in series. So it will become L1 plus L2. And capacitor C3 is also there. Okay. So it will be 1 upon square root of 2 pi square root of L into L equivalent into C3. So this L equivalent will be L1 plus L2. So what will be the formula looking like? So here we have L equivalent given by L1 plus L2, because we have a tank circuit looking like this, right? So we have a capacitor, then we have a inductor, and here we have another inductor. Okay, this is going over here, this is probably going to V out, this is going to the tank, this is going as a input to, this is going to the base terminal of BJT, this capacitor C3, this is L2, L1, this is ground. So L equivalent will be L1 plus L2. So the frequency formula will be given by 1 upon square root of 2 pi, 1 upon 2 pi square root of L equivalent into C3. Okay. So the frequency is changed by only changing the L and C over here. So please write down this formula. Okay. So we can change the value of F naught. F naught can be, frequency can be changed either by changing or varying L equivalent or C3. Okay, so we can vary the frequency by varying the value of L equivalent and C3. So why does the high frequency is obtained? Let me explain you why. Because see, normally L is in millihenry, okay, or it is in microhenry, or sometimes Henry also. C is in microfarad. So if you have a number, this is an example which I'm giving you all. If you have this 1 upon 2 pi square root of, let's say 1 millihenry, it is 1 millihenry. So 1 into 10 is to minus 3 multiplied by 1 into, let's say this is 10 microfarad. So 10 into 10 is to minus 6. So this is, becomes a very small number in the denominator. So hence F naught will be high. Okay. So this is the frequency of oscillations for Hartley oscillator. Please write them down. Yeah. Do you have any doubts? Hello. Anyone has any query? Because LNCs are very small, they are in the denominator. F naught can be adjusted to a higher frequency or a higher value. Okay. So some of the advantages, disadvantages we can write now. Can we? Okay, let's write them down quickly and finish it off. So some are the advantages. Write down frequency variation is quite easy. It can operate over wide range of high frequencies ranging from greater than 20 kilohertz to around 20 megahertz. Okay. So the frequency stability, it's poor over here. That means the nature of the waveforms is not purely sinusoidal. So let's write down the disadvantages, limitations. So the first limitation is it has poor frequency stability. So frequency is not stable with respect to time. It offers poor frequency stability. Another limitation is it will have loading effect problems, which will cause, it will result in a lower resonant frequency value. It will have loading effect due to the input impedance of the BJT. It will have loading effect due to, we can write over here, due to input resistance of BJT. Okay, this is just a point for your remembrance. Might be you will be understanding this point after some you're mature enough to understand the input impedance of the BJT, but it will have a loading effect problem which will result in a lower resonant frequency. Okay, and there is third point also. It has a low quality factor. Now quality factor is not been taught, so I am not writing it. Application wise, we can write applications. The last point for this circuit. Uh, they are widely used in RF range, radio frequency range. Applications in FM receiver. FM, you know what is it? FM, right? FM receiver. In function generators. In your lab, you must have seen a function generator and a CRO, right? And as local oscillator circuits in television receivers. So they have applications. Hartley oscillator have actually applications in these domains. Okay, and that will be the end of lecture number 1.